Hello and good morning, everyone. We're Group 9, and our project is titled Transaction Level Fraud Detection in Decentralized Finance. Our work builds on the BCCC DeFi Fraud Trends 2025 dataset from York University's Blockchain Cybersecurity Lab. My name is Kentrell Ziegler, and I'm joined by Whitney Holland, who you will see in a couple of more slides. Together, we are developing an end to end fraud detection pipeline that combines data analysis, machine learning, modeling, and interpretability. Today, we'll show what we learned from phase one, which study we're replicating in our progress towards phase two. Decentralized finance, or DeFi, allows users to lend, trade, and stake assets without intermediaries. But that openness has made fraud a huge issue. Over $1.8 billion in losses were reported just last year, mostly through phishing, rug pulls, and flash loan exploits. The challenge is that these fraudulent transactions often look perfectly normal on chain. Our motivation is to build a data driven, interpretable model that can detect suspicious activity in real time and strengthen trust in DeFi ecosystems.
Hi, I'm Whitney, and I'm also a part of Group 9. We're using the BCC Defraud Trans 2025 dataset introduced by Lake Shore. It's a tabular level dataset with about 1 million Ethereum transactions from 2017 to 2024. Each entry has 79 features such as gas usage, token flow, temporal attributes, labels are binary, fraudulent, or legitimate. Key challenges include temporal drift, mild class imbalances, and potential feature redundancy. These issues make it ideal for testing optimized feature selections, methods like the one we are replicating. Our phase one review covered 20 papers from 2020 to 2025, which we organized in four categories: traditional ML models like random forest and XG fast interpolables, but feature-heavy, deep learning models such as LSTM transformers, high recall but computational, expensive graph neural networks that learn wallet relationships with top AUCS around 0.94, explainable AI, fairness aware methods, which emphasize model transparency, the consensus, no single method dominates integral and adaptable remain the biggest open issues.
Phase two focuses on moving from literature to implementation. We're replicating the GA baseline proposed by Lashkari and others using the same dataset and evaluation setup. Our steps include building a clean data pipeline, putting into action the GA based feature selection, training baseline models, and validating performance metrics. This gives us a reproducible benchmark before we extend into new models in phase three.
We're implementing the pipeline entirely in Python using pandas, NumPy, scikit-learn, and det. We will load the dataset and inspect missing values, input the using median and mode, normalize numeric columns with z-score and scaling, encode categorical fields like status, errors, codes, split into 80 train, 10% validation, 10% test, keep it in chronological order to avoid data leakage. The output is clean, standardized data frame ready for feature selection and model training.
Let's kind of start to get into the numbers, a little bit of math in here. Our primary baseline is the genetic algorithm with penalty fitness function. Each individual represents a set of features out of 79. The GA evolves through selection, crossover at point 0.8, and mutation at point 0.1 for 30 generations. The fitness function rewards high F1 and penalizes redundant features, producing a smaller, more interpretable subset. The selected features train a random forest classifier. We also compare against logistic regression and gradient boosted trees to see how the GA baseline stacks up.
We'll evaluate models using standard classification metrics, accuracy, precision, recall, F1 score, and ROC AUC. Accuracy shows overall correct predictions. Precisions measures how reliable our fraud predictions are. And recall shows how many actual frauds we catch. F1 balance the two, and ROC-AUC helps compare models at different thresholds. All results will be averaged across 3 runs to account for variance. Here we summarize 3 representative papers: lecture, random forests, then we have allegorisis, XGBoost, and we have Zane. We went with lecture work because it's replicable and strong baseline. Our target is to reproduce F1 0.88 to 0.90 using the same metrics and splits. Once replication and validated, we'll move on to phase 3 extensions with graph aware and explainable models.
So we're at the end. Here's our progress update. Dataset access and cleaning are complete. Literature review expansion to 20 papers is done. GA implementation is in progress and baseline model training has been planned and staged. It's going slowly, but we are starting to figure it out a little bit with a little bit of time and research. We're on track to complete evaluation metrics and visuals in a few coming weeks. Our phase 2 goal is to deliver a fully replicable baseline with validated metrics. Our phase 3 focus would be to add temporal robustness and explainable AI modules. Thank you for tuning in to the Group 9 Project 1.5 update. Hello, we're Group 9. It's really great to see you guys again. Our Phase 2.5 update brings the paper we've replicated to the model advancements we've made and sets up our plan for Phase 3. My name is Kentrell Ziegler, and you will see in a few slides my partner, Whitney Holland, and we are going to pretty much explain everything that we've done so far in Phase 2. So we use the BCCC data set with over a million labeled DeFi transactions. It's purely numeric and it's great for supervised learning. The big hurdles are the imbalance in correlated cost related features, which motivated our genetic algorithm feature selection.
The reference study uses an advanced GA to pick a compact feature subset and evaluates it with a straightforward classifier, mainly random forest. We reproduced the GA approach and stayed faithful to simple classifier for evaluation, then extended with gradient boosting and soft folding in symbol to probe whether a hybrid improves robustness. The field cluster into four threads. Our baseline aligns with the evolutionary hybrid. For phase three, we'll add the temporal awareness, sequent models, and temporal splits, and if possible, graph structures. That's directly motivated by literature strengths and gaps.
And this is the fun part. We implemented an end to end reproducible pipeline, cleaning, scaling, genetic algorithm, feature selection with a penalty on subset size. We then trained random forest as a main baseline, and then we decided to add gradient boosting plus a soft voting ensemble, to which we saved the trained model, the GA mask, and feature names for fast reevaluation without rerunning the whole entire GA. Rerunning the whole entire GA took up the bulk of our time. It took us around 70 hours at first, and then we learned a few methods that could actually wane it down to anywhere around 7 to 15 minutes. So, on GA selected features, random forest is the strongest single model consistent with the paper. The random forest and gradient boosting ensemble is as good or a bit better, showing the GA subset supports more than one tree model. Feature importance highlights gas metrics, value, and the depth of interaction. Intuitive for DeFi fraud. Our confusion matrix shows a modest FP increase, which is acceptable to maximize recall. We're going to get back to these results a little bit later to address a little bit of data leakage and misunderstanding.
Our next step is to make evaluation time aware so we're not leaking future patterns. We'll palette a lightweight LSTM transformer on transaction sequence and compare against our GA plus RF baseline. We'll also test robustness across early versus later blocks and keep explanation hooks to remain interpretable.
So we ran a quick temporal split sanity check. And as expected, scores dropped compared to a random split, which means the baseline faces drift. Um, exactly why sequence models might help. If we have time before phase three, we'll lock a small LSTM prototype and report a fair apples to apples comparison. What we ended up seeing was that there was a lot of data leakage. We thought that the results that we actually got in phase two, where on our table you can see that we got 1.0s almost across the board, we thought that was a good thing. And then we actually took it to someone that was actually like a data scientist, and they told me that this is wrong because basically it's saying that it's perfect and there's no way that you got 1.0. So we're looking to fix that into phase three.
I would first like to thank Cottrell for being a such trusted partner in this project. He has worked so hard on the RF training, the GB plus RF minus the GB assembly features, importance, comparison, tablets. He's great. We communicate all the time. He calls me back. He answered the calls. He answered my questions. So I do want to thank Contrell for his hard work on this project. I've been working on the data cleaning, the GA setup, save artifacts, the pots, and write-ups. And for phase three, I'll be working on the temporal splits, matrix paper, and figures. Thank you so much.
Hello, everyone. Thank you for joining us for the last time for our project on the DeFi fraud detection using GA selected tree ensembles on the BCCC DeFi fraud transactions dataset. Our work is based on replicating and then extending the DeFi translizer pipeline proposed by Lashkari and their colleagues. Our team for this project is comprised of the two of us, myself and Whitney Holland, who you'll see in the next slide. In this presentation, we'll walk through the data set, the literature, and how we advance the original pipeline. And we'll also point out where our implementation work and experiments played a key role in the results.
Our data set comes from the Blockchain Cybersecurity and Compliance Consortium and Tabular Ethereum dataset with two CSVs, one containing fraudulent transactions and the other one containing legitimate transactions. After merging and cleaning, we work with a bit over a million rows and more than 70 numeric features per transaction. Things like gas use, gas prices, statistics, transaction values. We address counts and block lever aggregates. The target is a simple binary label, one for fraudulent transactions, zero for legitimate ones.
The challenges with the data set is just not clean out of the box. First is a strong class imbalance. Only about 8 to 9% of rows are labeled as fraud. If we just optimize raw accuracy, the model can do well by mostly predicting legit and still miss a lot of the fraud. Second, our correlation heat map shows big clusters of highly correlated features, especially among gas and cumulative usage variables. That redundancy can hurt training stability and interpretability. We handle this by dropping constant in all NAND columns, um, imputing missing values with the median, standardizing features, and later using a GA to select a compact subset of informative features.
From our expanded literature review of over 25 papers, we saw four main trends. First, traditional machine learning models like random forest, SVMS, and gradient boosting, after still strong baselines on engineered transaction features. Second, more recent work uses deep learning, LSTEMs, and even transformers to model sequences of transactions, but those models are expensive and harder to interpret. Third, there's a line of research that combines evolutionary algorithms like genetic algorithms with tree ensembles to select features to tune hyperparameters like Shikari's DeFi translator falls into the category. Finally, some papers push into graph neurals, network, and explainability, but they often require richer metadata than our dataset provides.
Phase two was all about rebuilding a clean version of the DeFi Translizer pipeline. We start by merging the fraud and legit CSVs, cleaning missing and infinite values, and standardizing all numeric features. Then we apply a genetic algorithm where each individual is a binary mask over the features. The fitness is the F1 score of a random forest under cross validation, with a penalty on the number of features. The best mask keeps around 15 to 20 features out of the original 70 plus. On this GA selected feature space, we train several baselines: a random forest, logistic regression, gradient boosting, and a soft voting RF and GB ensemble. A big portion of our effort went into the making of this pipeline and making it.
Here are the phase two baseline results on the held out test set with the usual zero point 0.5 threshold. The random forest has good overall accuracy, but the F1 score for the fraud class is only about 0.59, with recall around 0.42. Logistics regression is slightly worse. It doesn't capture the nonlinear boundary very well. Graded boosting and the RF plus GB ensembles give a small bump in the F1 and recall. So ensembles are clearly helpful. The confusion matrix for RF shows a lot of false negative, fraudulent transactions that the model still calls legitimate, that told us our pre processing and GA selection are mostly working, but the model, and especially the decision threshold, needed to be improved, which became the focus of phase three.
In phase three, the key idea was not to change the dataset or the pre processing, but to advance the models that sit on top of the GA features. We kept the exact same feature subset, train, test, split, and pre processing so that any performative gains could be attributed to modeling choices. We added two advanced components. First, a threshold tuned random forest. Instead of taking a fixed threshold of zero point 0.5, we sweep thresholds on a validation split and pick the one that maximizes the fraud F1 score. Second, we introduce XGBoost, a more expressive boosted tree ensemble trained on the GA selected features. We use scale POS weight to handle imbalance, and we search over the number of trees, depth, learning rate, and subsampling. The goal of phase three is to improve recall in F1.
This slide focused on the threshold tuned random forest. We took our GA based RF and swept the decision threshold from 0.01 to 0.99 on a validation split. The best threshold for fraud, F1, landed around 0.28. On the test set, this is a huge improvement. At the default zero point 0.5 threshold, we had F1 around 0.59 and recall around 0.42 after tuning to 0.28. F1 jumped roughly to 0.85 and recall up to about 0.74. While precision stays essentially perfect, the confusion matrix shows that what's going on, we accept a few more positive predictions, but we massively reduce false negatives. Many more fraud cases are correctively flagged. This is a nice example of how a simple threshold tuning.
Now we add XGBoost to the mix. Using the same GA selected features and class imbalance handled via scale POS weight, XGBoost achieves accuracy in the mid 0.8s and an F1 score in the mid 0.7s on the test set. Its confusion matrix is interesting. There's almost no false positives, but we see more false negatives compared to the tuned RF. That means XGBoost is more conservative. It rarely cries wolf, but it does miss some fraud. When we compare the two, the tuned random forest still gives us the best F1 in recall. So it's our top model if the goal is to catch as much fraud as possible. XGBoost is attractive in scenarios where false alarms are very costly and we're willing to miss a few more fraud cases. Overall, both advanced models clearly beat the phase 2 pipeline baseline, and together they.
On this slide, we're showing you how we divide the work. I focus mainly on the research and the writing slide. I let the expanded literature review organize more than 25 papers into the four modeling categories we mentioned earlier: traditional machine learning, deep and sequence models, evolutionary and ensemble methods, and graphs, explainability focused work. I also wrote and revised mixed part of the introductions and the literature review sections and helped shape the methodology and results narrative. So the paper tells a coherent story. I'm also the one who helped design and polish the slides for this presentation. Contrell handled the heavy implementation and experimentation. He built the slow GA training notebook and the fast evaluation notebook, set up the full pre-processing and feature selection pipeline, and implemented all of the models, random forest.
All right, so our main takeaways are: first, the combination of GA feature selection and tree ensembles is a strong, interpretable baseline for DeFi fraud detection. Second, a very simple technique: threshold tuning on a validation split dramatically improves the fraud F1 and recall for random forest without sacrificing precision. Third, XGBoost gives us a different precision recall balance and shows that boosted trees are a promising direction if we want to adjust how aggressive the detector is. For future work, we'd like to move toward temporal and block-based evaluation, explore graph neural networks on wallet interaction graphs, and add explainability tools like SHAP, SHAP, so that analysts can better understand why each transaction is flagged. Thank you for listening, and we really appreciate your time.